Today we'll look at beginning of chapter 13, and we'll start with area under a graph. So we start with this picture. So this is from the textbook. So this is a time velocity graph where you have time on the first axis and you have velocity or speed on the second axis. And this graph actually describes the distance that an object travels. So I'm just wondering if you can envision how this object actually moves. I mean, when time is 0, that would be the starting point. And this is measured in hours. So we have a straight line for 4 hours. So what does that mean? Well, it means that it moves at a constant speed. So the speed is 8 kilometers per hour. And then this line drops, and this object is traveling for another 2 hours. And what we see here is that the velocity goes down. So if you have something, I mean, it could be a Mars rover or something, yeah. And it goes at a constant speed for 4 hours, and then maybe the battery is winding down, so it goes slower and slower and slower and slower until it finally just stops after 6 hours. So how far does it travel? Does the graph tell us that? Well, not directly, but indirectly it does. So what we can do here is we can split the graph in 2 parts. So if we sort of make a split here, we could look at the first 4 hours. So, I mean, the question is here, how far does this object travel? By this, we're talking about this object that sort of moves along this curve then. So we can answer this question in 2 ways, and we'll start looking at the first way of finding the answer to that. So we split the graph in 2, the first 4 hours and the last 2 hours. And for the first 4 hours, we have, okay, just going to check that message. Is that from any of you? Nope. Or, nope. Okay, that's fine. Just hang on 1 second. Right. So the first 4 hours, this object travels at 8 kilometers per hour, which gives a distance of, well, let's think about this. Okay, so you go for 1 hour at 8 kilometers per hour, so that's 8 kilometers. And the second hour, you go at 8 kilometers per hour, so that's 8 more hours. So you can just add together the first 4 hours, and that gives you a distance of 32 kilometers. So this corresponds to I mean, this actually corresponds with the area under this graph. If you look at that, you have 4 hours and then you have 8 kilometers per hour. Now, so how many squares do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8. And if you add them all up, they add up to 32. So the distance actually corresponds to the area under this graph. Now, for the last 2 hours, the starting speed is 8 kilometers per hour. And the end speed is 0 kilometers per hour. So clearly the answer is not 8 and it's not 0, so it must be somewhere in between 16 kilometers and 0 kilometers. Right, so it's not 0 and it's not 16, so it's somewhere in between. And if we also here consider area under the graph as an answer, we could examine the area of this triangle. So the height of the triangle is the speed, so that's 8, and the bottom line of the triangle is 2, because that's 2 hours. So if we want to find the area here, that's going to be 8 multiplied with 2 divided by 2 is 8 kilometers. Now, we haven't really established that this is a reasonable way to do this, but we could, oops. We could use this as a preliminary answer that the object travels 32 plus 8, so 40 kilometers. Okay, so that's one way of answering this question. We could look at another way to answer it. And let's just assume that for this graph, distance will always be area under the graph, because we know from physics that distance equals velocity multiplied with time, or d equals v multiplied with t. Right, so we can put a frame around that. And I mean, we can also see this from the units. If you have something like okay, 8. If we look at the first 4 hours, we have 8 kilometers per hour, so that's the velocity, and then we have 4 hours, that's the time. And if we multiply the numbers, we see that that's 32. If we look at the units, so here you have hours underneath at the bottom of a fraction. Here you have hours at the top. So we could sort of delete these against each other. And what we're left with is kilometers. So, So that would suggest that, okay, this formula actually works because the units add up as well. Now, if we look at the rest, I mean, what we did in the previous example here is that we actually found the area under the graph, and that seems to be cool. Now, later, we're actually going to expand this into a universal result. So this not only applies to these straight line graphs where you have straight lines. So this is really a split function where we have one function for the first part and then another function for the last part, and we can find the area under the graph. And it's not that difficult because we know how to find the area of rectangles and triangles. But it also applies to curves, and that's the important result here. Now, so I'm going to pause the recording in a minute now, and I'll let you consider this square at the bottom here, the green square. How do we interpret that square? What is the unit measure of that square? So what does this square represent? What does, oops, the, oh, at the bottom of my screen, that's why it doesn't write that well. What does the green square represent? Okay, and we'll take a minute to try to answer that question.